Good evening, Vandana. Hello.
Yeah, good evening, sir.
Okay. My voice is audible?
Yes, sir. Yes, sir.
Okay.
Yes, sir. Yes.
Good evening, Vandana. So today we are going to start the day 2 ATAL FDP. So today the chief guest is Dr. Sandeep P. Patel. So I'm just reading. I'm giving the intro about the today's chief guest. We are honored to welcome Dr. Sandeep P. Patel as a distinguished speaker for the ATAL Online FDP on AI and Simulation in Additive Manufacturing. Academic and professional background. Dr. Sandeep P. Patel is the director of the RWTH India office and a group leader at RWTH Azan University, Germany, a position he has held since 2015. He is also an adjunct faculty at COEP Technological University. He completed his Master of Science in Computational Mechanics of Materials and Structure from the University of Stuttgart, Germany in 2010 and is completed a PhD from RWTH Azan University in 2015. His expertise and contribution as a director of the RWTH in the office, Dr. Patel is responsible for selecting the MSc and PhD candidate for RWTH Azan University and collaborating with the universities and industries to drive research and innovation. His research interests include continuum mechanism and molecular dynamic simulation, multi-scale modeling and advanced materials, brittle fractures and material forming, biomaterials. The achievement and recognition of Dr. Patel is the recipient of Scholarship 2010 for academic excellence with the extensive international research experience and a strong background in computational mechanics and advanced materials. He continues to contribute significantly to academia and industrial collaboration. We look forward to his insightful section and the valuable knowledge to bring this to the FDP. So thank you one and all. Now I'm going to hand over the section to today's chief guest, Dr. Sandeep Patel. Sir, once again I welcome you, sir. Now you can take the sections.
Yeah, thank you very much. Am I audible?
Yes, sir.
Okay, yeah, thank you very much for the nice introduction, and I would be happy to share my screen so that you can see my presentation. Can you see my screen?
Yes, sir. Yes, sir.
Okay, I hope so. You can see my screen in full presentation mode.
Yes, sir. Yes, sir.
Yeah. Okay. First of all, thank you to Aditya University, with whom we have already collaboration, and we have been working together with the student exchange and other possibilities to carry out the starting with the student exchange to research activities and other plan activities with between these two institutions. So first of all, I would like to, before I go into the topic of numerical modeling of high-speed forming techniques, I would like to go into the details first with university. So I'll talk about RWTH Aachen University first part, and then I will go into the main topic of the today's session. So RWTH Aachen University, you must be knowing it. If you're in a manufacturing and mechanical thing, then I think it's one of the best in the whole world. So if you look at the QS ranking 2025, the QS ranking of this university overall is 99, so it's in top 100. However, if you look at the specific subject wise, mechanical, for example, aerospace, production and manufacturing, it's ranking 19, 19. So in the whole world for the according to the QS World Ranking 2025. If you look at the another ranking, like Workshop Oka is one of the financial journal, which is pretty much famous for the Europe, which is ranking first for the industrial engineering and second for the mechanical and electrical engineering. So we have been working extensively into depth with the engineering sectors mainly. So if you look at the one of the group of technical university in Germany, so typically we have 7 IITs. as well as if you look at the US, it has Ivy Leagues. So similar to that, we do have a TU9 in Germany. So top 9 technical universities in Germany, and it is a part of it. So RWT is a part of it. Also, it is a part of the Excellence University cluster. Also, it is part of the Idea League. So it's nothing but 5 leading European universities of technology. For example, Chalmers, as well as other universities are coming under this Idea League. So which is a one of the elite league for the technical universities. We do have a strong collaboration with the international top level universities. So I'm going to talk about the India. Then we do have a strategic collaboration with IIT Madras. Yeah, just to give the numbers, so we do have more than 47,000 students on campus for our different programs. Out of these 47,000, 12,000 plus international students. So we are talking about the almost 25% students are international students, and they're coming from 138 countries. So diversity wise, it's immensely high compared to the other universities, I would say. We are getting every year almost more than 6,600 graduates. Every year we are getting new enrollment of 10,000 plus students. We do have a staff of 10,000 plus, more than 553 professors, and we do have 9 faculties. So if you look at the institutes, so institute like acting as a small scale industry, small and medium scale industry independently under the umbrella of RWTA. So we do have more than 260 plus, and university budget is 1.1 billion euros. I think microphone is on. Somebody's microphone is on. It's like getting echo. Okay, so total budget of this university is 1.1 billion euros, and out of this 1.1 billion euros, 50% budget is coming from the third party. So third party funding is very important in order to carry out the research beside the public funding or government funding. And this is coming from the different companies. So you just name it and you will find find the collaboration of the company with RWTH. So starting with the Gary Weber to Porsche, Mercedes, Daimler, all of them having really strong collaborations with the RWTH Aachen University. So if you look at the distribution of all students in Aachen, we are almost more than 65% students are coming from the engineering faculty, and remaining from the science, economics, and we also do have the medicine faculties also. Okay, so if you look at the international students, China is topping. It's around with 21% of Chinese students. Second best is the Indian students, which are around 12 to 13%, which is a really good number. But from last a couple of years, this number has been increased significantly, and this is a really good sign for us also to have the more Indian students or good quality Indian students for our master's PhD programs. And there are many other countries from where we are getting the international students. Okay, just to give the idea, where is Aachen? Aachen is at the triple countries border, so it's pretty close to that and Belgium. So it is called as a center of the whole Europe. And if you look at the history also, King Charlemagne he used to live in Aachen, and who used to handle, or let's say rule the whole Europe. So his place, or let's say stay, was at Aachen. So from Aachen, if you would like to travel, Amsterdam, Rotterdam, as well as Brussels, they're almost like a 2 hours or 2 and a half hours. So if you look at Paris also, it is like 3 hours, 3.5. Berlin, Hamburg, then Munich. These are the also not far away cities from Aachen. We do have a RWT India office in Pune now, and the main idea behind this office is to have the in-person presence in India. and the main responsibility for this office is to select the best quality of student for master's degree program. Also, we are offering also internship for the potential MSc or master students who plan to go to Aachen. Also, we are providing scholarship and research guidance to bachelor as well as PhD student. And another important responsibility of India office is to have the research-based collaboration between RWTH and reputed Indian university as well as industry. So we are in Pune in person. So if someone is willing to visit us, they are always welcome. I will provide at the end contact details. Okay, so today's topic was numerical simulations of high-speed forming methods. So we used gas detonation forming. So in my first research, I used gas detonation forming, and second research, I used the rapid compressive machines. So I published more than 3 articles into this area. So you can take a look on it. But I just present one work out of it, so you can get the picture about the high speed forming and how the method works and what are the numerical techniques one can use it in order to have the better clear picture at the section wise, or let's say at the more detailed way compared to the just experiments. So gas detonation forming, it is the high speed forming method. If you, I would explain it in the next slide also, but it is like direct explosion or contact of the gas mixture on the sample. Um, and this gas mixture, or let's say waves or detonation waves, are traveling with supersonic velocity. And this high speed velocity waves are deforming or forming the components into the shapes. So if you look at the top right uh, image, it is with a tube joining with a different diameter. So let's say these are the big diameter and small diameter. If you provide the detonation wave here, then it is just going up like this and then trying to form the connection with each other. Now the another interesting one, tube joining with the different materials. So you can have this different material with the grooves, it just fitting it on each other, but there is a gap always, of course. If you have the high speed waves and if there's a blocking at one end, then the pressure is applied in lateral direction, and then lateral directions are going into the grooves, and then you can see the copper tube and tensile steel, they are joined together. So if I look into the details, you can see that in the grooves the copper metal has been gone, and then if you try to pull it now, then it is nearly impossible to get the detachment of these two tubes. So this is one of the application of this method. Another application is tube expansion. In some cases, you would like to have this certain portion of the tube get expanded, so larger diameter, or let's say different kind of shapes or expansion in the certain dimensions. Then you can do that. So which is called a tube expansion. So what are the advantage of this gas detonation forming? So advantages are, it has the potential to form the complex shapes. So if you look at here also, even the tube joining, you can see that the metal is going into the grooves nicely. So therefore it has, this method has the potential to make the complex shapes. Embossing, embossing means like you are putting some coin or something which has some kind of letters or something like that. If you put the material with a high speed onto it, and then material get deformed, and then you get that shape, which is a like embossing on that material. It is reducing the wrinkles, which is generally you'll see that in the low speed forming methods, and spring back effect. So it's reducing the spring back effects quite significantly. I'll explain that in the coming slides. It is a clean combustion. It's a H2 and O2 combustion. So it is clean, no pollution. and fewer safety regulations and easy automation from this method one can see. So it is easy to use it. However, a huge setup is required. I'll see that if whether I have showed here, but it is like a huge setup needed. It's like a huge tube, and at one end you are putting the sample, and other end you are doing the explosion. I'll show you with one image here. So here you can see the ignition of H2 and O2 at one end. So here you can see that ignition is happening at the left side of the tube, which is the ignition force which is created due to the ignition of H2O2. Then afterwards, detonation wave started because of the ignition, and this pressure wave propagation is happening. And then you can see the flame front, and which is compressing the heated gas, and that's become creating the pressure waves. So you can see in the right side picture how the pressure waves are created. And on that end, so right hand side end, there will be a sample, a blank, which is you would like to deform into the different shape according to how you put the die at the end. And again, there's one more thing, which is a reflected wave, which is coming again from the reflection of the sample after the impact, and then again it's getting reflected and again hitting back. So this is what you will see with one pressure wave diagram. Okay, so again, application of this method, or let's say this forming forming method, can be into the computer control detonation spraying process, tube joining, cup forming pipe, and variable with a variable cross section that you have seen already in the previous slide picture. Okay, so in Aachen, what we did was to have the experiment on the one blank. Initially, we had this DC04 steel blank, and which is we put it into the grooves. So I'll just show you here. So we just put it into the here the tube and the dia. We put this blank here into the groove, and then the somewhere here there was a pressure created with the H2 and O2, and detonation happened, ignition happened. Then it created the lot of pressure. Generally, there is always diaphragm. So you all must be aware about the diaphragm, which is a again cutted sections of the one standard blank. So in order to have the high pressure on the detonation side, so once that pressure is created, which can break the diaphragm, so that means it is the diaphragm is providing the time in order to create that amount of pressure. And once that certain pressure is reached, this is breaking the diaphragm, and then it detonation waves travel, and this detonation wave travels and hitting on the blank. And then this is depending upon the pressure how much you are applying, it is getting into the shapes here. um, so for our experiment, what we wanted to have a cup formation. So therefore what we did, we filled the gases of H2O2 with initial pressure of 30 bar, and we ignite the gases at one end in order to create these detonation waves. If you look at here, even though there's one die, there's a die holder is also there, because it's creating huge pressure. It is from 30 bar to almost 150 bar. So it's a huge amount of pressure is getting created into this method. So therefore we have also die holder, and which has a vacuum vent, so which is putting at the bottom, and which you can make sure that there is no pressure or negative pressure is created at the end, and which is making the issue to the blank in order to not to form the correctly in the shape. So therefore we made this vent, And as I said, the inner dimension of the dia was like 54 diameter, outer diameter 30 millimeter, inner diameter, and then other dimensions. So I'll just show you the next steps. So here, the pressure behind the detonation waves exceed the 20 times of the initial pressure. If you look at the initial pressure is 30 bar, but peak pressure of this experiment is going up to 150 bar. So measurements we made in this case in the experiment with a piezoelectric sensor. And as I said, we avoid the negative pressure by using the vacuum tube, and sometimes we put it like a moisture filter paper on the blank on the gas heating side, so that there is no overheating of the blank at the surface. So if you look at the pressure in a very short time, you can see the peak pressure of 150 bar, and then afterwards it's going to lower side again. It's because of the reflection wave. Again you get the little more pressure, and then going down again, going up and down. So this is what the pressure wave we have observed. If you look at the modeling, or let's say finite element simulation, in which we use LS-DYNA and we use hypermesh in order to create the model. So in hypermesh we created the model, and you can see here, this is the model we created with the CAD. We meshed it using the hypermesh. We use different types of models. So we use one 2D model, which is just like a one blank, and then shape of the dia. It's like a 2D model, but it wasn't showing much things because of the lateral pressures and other things, and we wanted to also study damage. So therefore we didn't consider that as a that as the main model for the study. So therefore what we did, we just considered quarter of the system. We modeled it, and we put the axisymmetric boundary conditions. So you can see here, this is a dia, this is a dia holder, and this is the sample blank, which is a red color. So when and we applied the pressure on the portion which is open to the gas detonation. So this is what we did it. And now, so it is very standard practice to use the dia with the solid rigid elements, which is like called as a MAT20, because it's not the active part in the simulation. So we don't want it to have like any other material, which is then calculation will be there, and it will be like too much simulation time. So we use these rigid elements, and we put it like a high stiffness, of course, and it is not the active part. So we are not interested into die, but we just made it into solid rigid element. Blank, this is what our interest, which is use Belasco t-shell shell element with 1 millimeter thickness. We tried with the other shell element also, but as you can read into details, this Belasco Tishe is the element type which is perfectly suitable for our high-speed method. So simulations were done using the material models of MAT03, MAT24, Johnson Cook material model. So if you look at the kinetic hardening, which is very simple model, I will explain it in minute. Material properties we assigned to the blank was still DC04, as I said, and still DC04 mechanical properties are elastic modulus, Poisson ratio, density, and tensile strength are tabulated in the figure in the table. So we use the first one is kinematic hardening, which is very simple one. So straight line and then going up. So with some kinematic piecewise linear elastic plastic. I think many of you must be used this, which is always putting the stress strain curve to the software, and then this is how it's making its behavior. So different strain state uh, were considered directly from the experimental data of Professor Ferlesen from Belgium. she carried out so many experiment with a different strain rate, and we used that directly for our experiment for our simulations. And the last model what we used was Johnson Cook phenomenological model. This is very interesting. So just to not to go into detail, because this is like um, I can explain that how we can get the parameter of the Johnson Cook, and in our paper also you can find it, this material model explained in more detailed way. So parameters A, B, and N. If you look at here, A, B, and N are yield stress, hardening modulus, and then C is a strain rate factor. They are N is the strain exponent. These are the parameters determined using the static tensile strain test. So it's not like rate dependent, but the other parameters like a C and N. So if you look at the strain rate factor and the temperature exponent, if it has the temperature uh, role in playing into it, then it is like calculated using the high strain rate tensile strength. Means some of the parameters are calculated with the static strain, and some of the parameters are calculated with the high strain rate. So what was the gap between the research? What we have seen was, in previous studies, most of them they consider the triangular loading. So what you can see with the red line and blue line, they never considered the high loading rate, and this is what the first peak, and they were always missing it. So therefore, that was our main focus, to see is this first peak point is the most influential peak for the deformation or not. So what we did, we checked the experiments, of course, 54 diameter to 44 diameter. We observe, we can see that nice shapes, as well as we can see some embossing at the end, and we see no spring back effect, no wrinkles observed on the flank and cylindrical skirt. So therefore it was perfect with the experiment. Now what we did with the experiment, we carried out the experiment and we found that outer diameter wasn't 44 exactly, but it was 46, which was pretty close. There were no wrinkles observed, as well as what we see with respect to time, it was going nicely into the um, dia, and at the end you can see that very sharp going into the corners and making the exactly shape what we observe experimentally. So if you see here, exactly sharp corner ones what we observe here in the simulation. So that was a very interesting for us. And important the parameters what we want to study, which is uh, many people also studied, is thickness distribution along the from the exterior edge to the center of the blank. And what we observed, so what we did it, we cut down the sample, deformed one, and we started measuring the thicknesses, and that's what we plotted with a circle, which are the experiments. And then we carried out the simulation, and then simulation thickness distribution, we checked it, and we found that the first impact is making or plus peak load is making lot of deformation. And this is where you can see that green and black curve, which are almost getting nicely with the experimental data, especially black one, which is pretty close to the experimental data. And you can see that there is also nicely prediction of the thickness value at the 90-degree bend, as well as decrease in thickness in the both side of the bend, as well as it was well captured. And also there is an increase in wall thickness also you see in the right hand side. So this was interesting for us. Also we studied the damage also. So if you look at the first figure, so it was for the low loading. So let's say detonation not happen correctly, diaphragm was ruptured abruptly, then we saw that this kind of behavior, and we compare with the experimental values, experimental things also. Then we carried out the medium load, which was the perfect with to form this kind of sample. It was perfect. Then also we carried out little bit extreme pressure than the 150 bar. Then we found that there was a damage, and you can see here also. It is interestingly, you can see this damage happened here, and we could predict it at the sharp corners at the bottom, and it was interesting. And then we also went again the high extreme pressure, where the blank was at the bottom was almost like flew away. So this is where we observe also in the numerical simulation. So what we did with this also, we considered the different stacks of the plates of the different materials, aluminum, copper, and steel. We put it together, made the detonation. We also considered the different shape, tube joining. Also, we studied, we did the numerical simulation also. We also used the rapid compressive machine in order to have the similar kind of test. And yeah, we published these 3 4 articles, which you can take a look into it. So to summarize it, so numerical simulations were carried out with the different material models in order to see the reproduction of the experimental results as close as possible. We use Johnson Cook material model. Our finite element model can predict the cup shape of the blank, including the sharp edges at the bottom corner, which I showed you. Thickness distribution pattern exactly similar to the experiment. Then yeah, we found that the sensitive loading rate things into our simulations, so which you can see that nicely smooth results, which you can see from the low loading rate, a triangular loading, and when you go to the reality, it is like extremely fluctuated load. Then again, we can see that accurate measurement of the loading rate is very important in order to have the exact similar simulation results. Um, we also studied the different shapes and geometries using the FE model in order to give the idea about the without experiment to how it form and how it can be give the results also. Numerical study concluded that which has a negligible effects on the experiments. Therefore, we didn't consider the temperature effect into the Johnson Cook material model. These are the references what we used for our study, and yeah, there are some articles which you will find it in my research scholar in order to see. Apart from this, I would like to show you some glimpse of our recent research. So generally what we do at RWTH, we do have a theoretical modeling, which is like theory. Then we do the numerical simulation and experimental validation. So research has these 3 pillars. Then you get really good articles in high impact journals. So we worked on the sheet metal form, this cushion seat with a coupling problem with the different fields together, crack propagation, brake pad, then fracture, and then even you can see this breach kind of things with the stresses points. Um, then I would like to show you my PhD research also, which is, you can see here the biomaterial spider silk as a airbag fabric material, which is a can be potential one. So if you look at here, so simple thing is with airbag right now, the people are using nylon 66, which is a highly elastic material. But if you have some dissipation into it, you can get the lower HIC. So lower the HIC, which is called the head injury criteria index, which is lower, then it's better. So we found that the airbag is a better material, and we have been carrying out the some of the experiment at the our textile institute. Our research got noticed with many journals. So recently into 2020, we got 2 articles which are on the cover page and cover stories. So you can see here in the right side. Just to give the glimpse of RWTH, we have been not just technically putting a lot of efforts, but you can see here our extra activities with the technical projects as well as fitness things. You can see here. Also, we are celebrating the many festivals, Indian or doesn't matter that the period and a lot of celebrations with seasons. You can see here also cycling and then winter also. Of course, RWTs is always welcome to people to study and also to do research at campus. So with this, I would like to thank you very much for your time and patience and listening to my talk. This is our contact details, so you can get in touch with us with emails. This is the best way to reach, as well as you can find our office number, and you can find our find us on Insta as well as LinkedIn. Now I would be happy to answer your questions if you have any. Are there any questions? It seems like no questions.
Hello, sir. I request to please share the slide with us.
Sorry.
Sir, I request to please share the slide with us to participate.
Yeah, I can share these slides. Yeah, I need to put this as a copyright thing, and then I will send it to you or a concerned person by tomorrow. Is it okay?
Sir, one more question, sir. Yes, sir. Sir,
Yeah.
still a lot of the research working going on in additive manufacturing in different various fields, from metal to non-metals, from aerospace to the pharma, food processing. So in which sector they are playing more role in the field of additive manufacturing till now?
Your voice is breaking too badly. We
I am
can
saying
hear
that.
you.
Sir, now I am audible.
Hello. Hello.
Now I am audible.
No, sir, not at all. Actually, it's too much breaking your voice.
Manish sir, please check your coverage area.
Yeah, this is perfect. Perfect voice.
Your voice is clear.
Now it's clear. Somebody's voice is pretty clear now.
Hello, sir. Am now audible?
So it's like a lot of frequency variations. It's I think could you please check your network and could you please move to the strong
Okay, you can
network?
type the in message chat box. You can type the question, sir. No problem.
That's also perfect for me.
Chat voice is disabled, I think. I am unable to type in chat box.
Hello. Yeah, but yeah, that's
Hello, sir. Will you enable the chat box? I'm asking to the coordinator because chat box is disabled. Or am I audible to you, sir?
Just 1 minute, sir. You check it. Just 1 minute. We are just keeping open chat box. Just 1 minute. Just 1 minute. Just check it once now. Check it once, sir. Please, sir. Check it once.
No, sir, it's still see, it's disabled.
Your voice is
amount-
audible to me clearly. You just ask again, please.
Hello.
Hello.
Yeah.
Yeah,
So
this is
my
Dr. Sachin
question,
Pandey from MIT Gwalior.
Yes, sir. Hi. Good evening.
Good evening, sir. Just a few questions regarding additive manufacturing, if you can just answer. What are the materials that your institute is currently working in terms of additive manufacturing, the recent materials that you are working with?
Yeah, I also worked into this same area, additive manufacturing, but we worked with mainly with the plastic material. Of course, I wrote one review. We wrote one review with putting it all the things together regarding the flaws and fracture and these things. But mainly we are working with the plastic material in order to have these things. And our one of the Fraunhofer institutes, they are mainly into the additive manufacturing. They are using metals and other kind of materials in order to do the additive manufacturing. But we are working mainly with the plastic.
Okay, that means you are working with FDM only. Okay.
Yeah, yeah.
So what the institute, that collaborative institute, I'm not getting. Your institute is working on material.
No, we are not working directly on it. It's a Fraunhofer. If you want, you can please write me an email. I will send you the details about the institute which is working on the additive manufacturing dedicatedly, and they are working with a variety of materials. I'll send you the details. So that will be good for you.
Actually, your last screen was not so visible, so that I can connect you regarding with the email. So if you can just please share it once again, then that will be okay with me.
Yeah, sure. I'm not a problem.
The only problem is that because most of the institutes are working with plastics and only, and
Right.
uh, and
I
uh,
see.
plastic is kind of very
Yeah. Can
common
you
nowadays.
see my email IDs?
It's still not so clear.
Oh, I already shared the screen.
Okay. I just request the coordinator to please share this recent PPT, this slide only, this particular slide.
Okay. Yeah.
If the
Okay.
coordinator
Okay.
can do it.
Yes, I'll send it then. Yeah.
Everyone, there is one option, question and answers. There is next to the chat box. You can type your question here. It's visible to all.
my chat box is not enabled. I'm still finding the chat box is disabled.
Now your voice is it's good. I mean, please go ahead with your question.
Okay. So my question is that I attended a session in the last minute, so I have not it properly get the. So my session is the the research working going in additive manufacturing in various field. So in which sector the AI implementation is higher in additive manufacturing? Which sector of additive?
I mean, recently, I've been working in a silica aerogel also. It's like a highly nanoporous material. I think this is a new area. So porous material, I would say, roughly. This is where I think it's going to be uh, highly uh, important area in the coming years for the additive manufacturing. Lot of chemistry required for forming silica aerogel. However, recently the Nature Material paper, which was showing that it is so additive manufacturing can produce the same thing what you observe from the chemical reactions, and doing it for let's say weeks, the end product what you received as a porous material, that you can do it with the additive manufacturing. Of course, they didn't get the same strength as they form it with the sol-gel process, but important point is they can reproduce the same structure as it is, and it is getting better and better with different nanoporous material. Even I saw recently the lot of research into the aluminum nanoporous material. So I think these are the areas I would highly recommend to focus on in order to have the good articles and good research, I would say.
So which material are widely using for making porous?
Sorry,
Which
which material?
material there for making porous structures?
They use plastic.
Which plastic? Regarding, see, I am working here in CPET Jaipur, which is a center for testing of plastic materials.
Mm-hmm.
It is a institution come testing center of central government.
Mm-hmm. Yeah, if you want, I can share that details with you.
Okay.
Yeah, please write me an email so I can provide the details to you.
Sir, your last slide is not properly clear to us.
Okay, I'll just
We are
copy the.
unable to get your information.
I will send you the. Of course, I will send the slide also, but also I will send you the presentation also, and I can see here if I can type it.
The thing is, most of the researchers working in the additive manufacturing are concerned about the materials that we are using. We have learned about ABS, PETG, and many other, but we are concerned about the things which are currently being used in the as a recent research in the field of additive manufacturing. So if you can just share the details of materials which even in the sense of polymer also, that will be good for us. That's what sir is asking.
I actually, honestly, I don't have expertise into this field, so we did the study, but not from the production side of production side. But what we studied is after what happens after the making the material with the different let's say raw materials. We studied the flaws, what kind of flaws, how much the dimensions, and what is happening actually with the chemical reactions, as well as how's the effect on the mechanical properties. We studied that with one review articles, and which got really good attraction among the all the researchers. We got almost more than 350 citations for the same paper. I can send it to you, but it is the second part, like a post. Pre is not where I do have the expertise, honestly.
Okay. I request the coordinator to please share the last slide of Sir Sandeep sir.
Yeah, I already texted the my contact details in the Q&A part also.
Sir, can you share the last slide? Only last slide, the contact details. Can you share your screen so that participant can see the contact details?
Yeah, actually I did it, but I cannot do it again also. Can you see the slide? Last slide? Can you see the
So
last slide?
So enlarge the last slide in slide mode, presentation mode. Because when you are sharing this slide, it is blurry.
Now it's okay?
Yeah,
No,
number
sir,
is
still
visible, sir.
your mobile number is visible.
Yeah, I already sent into Q&A session the details about the emails.
Okay, participant, I will send the details. I will take the details from the Dr. Sandeep Patil sir, and I will share it later.
Yeah, sure.
Remaining people who are having question, you can ask the question.
Yeah, seems like no questions.
Sir, I have one basic question.
Yeah, sure.
Sir, I have seen your papers and especially the Germany side universities, they're having more research work towards numerical modeling instead of using the finite element method, FEM based ANSYS, SSVL, or the softwares. They worked on the coding part and the equations part. They try to more on that one. So how this kind of a culture is really important from the Indian research point of view? Because in normally we have seen in Indian universities,
Yeah,
we are using a
I
lot of
can.
free available software.
Yeah, so I mean, it's like a black box, Elestina solver, then Abacus and everything. And this is a black box. We don't know what's calculation going on. Okay, we know that what we are putting, and we know that from the research, let's say the company people, what they're telling, what's going on in the model. So therefore, in order to avoid that black box concept, everyone, we do have also in-house software which is calculating exactly the equations of that material model. So it's all about finding out the deformation gradient, then strain, and then stress. So it's very simple coding. Of course, it gets complicated when it goes to the optimization. It takes time, but we do have this supercomputer ability so that we can do the fast calculations also. But it is very typical of having the in-house coding in order to do the finite element simulation on our own. And this is very important because you don't then make mistakes, or let's say you don't assume some of the things which are you don't understand. So if I look at my in-house code, then it's very pretty simple. It is like line by line I can get out the outcomes, and then we can cross check it with a theoretical calculation.
Some free open source softwares are available that can supports for changing the
Not
equation. Like
not
FlexPD is the Ali was using that one now previously.
Yeah, Flex is with Stuttgart, so it is not available. It's not open source. Of course, it is open source, but in-house in Stuttgart. This is where I also studied. So therefore, you need to have the license. But it is like a solver, so you can buy the license also FlexPD. But it is like, as I said, it is completely developed in-house. So you know what you are going to get it out. You know what you are calculating.
So, sir, it means that if you want to simulate one particular area in additive manufacturing, and I want to build one complete solution for software solution for that one, so we have to write complete codes in one particular language, like C or Fortran something, and then we have to check it. Am I right?
Yeah, or you can develop with computer science people in-house code, and then you can go and use it for the different applications. Additive manufacturing is one of the example. Made high speed forming, even tensile test, shear, twisting, all test you can do it. Perfect. It seems like all questions are answered. So thank you very much, specifically Dr. Zubuddin, who has been in good touch with me. So thank you very much for your support, and thanks to the audience also, who has been very patient to listen to this talk. And I would try to share my articles also with doctor, and then I think he can distribute around.
Okay, sir, you can share. I will distribute to the participant. Thank you, sir. Thank you so much.
Thank you very
Your
much. Thank you.
valuable slides and your lecture, sir. And I hope so, audience, there is no question from your sides. Thank you, sir.
Yeah, thank you very much. Have a nice evening. Bye.
Participant, actually, because of some time limitation, Dr. Patil sir is having so he has finished then up to within 7 o'clock. But our next session will start at 7:30 only, because the next session time is allotted to the speaker at 7:30 only. So I request all participants, please keep login. And when the next session start, I will ping in the message also, and I will send the message in the group, and in meeting also I will inform you. Please keep logging. Thank you. Our session will start at 7:30. Next session.
Sir, feedback.
Feedback form I will share soon.
Okay, sir.
Regarding the PPTs and content information, I already sent in the WhatsApp group. There's Sir Dr. Sandeep Patil sir email ID. And regarding the phone number, once I will confirm with him, then I will send it, sir. I think it was visible on the last slide, sir, or I requested sir also to show the slide. I will confirm again, sir, and then I will share the mobile number also, sir.